Good afternoon. Welcome to the final, unfortunately, the 6th plenary session. It's a very exciting one as well. Hi. We'll be seeing together two important talks, one keynote and one visionary. We also have a few things in between I'll cover with you when we reach there. To start with, we do have a keynote talk by Andreas. Andreas Aal has been with us for 5 days already. He probably met all of you so far, even though he comes from somewhere that's not very strongly linked so far with ITC. He comes from Volkswagen, from Germany, the Volkswagen Group, where he has been very active. And for me, it was a surprise when I first got introduced to him. He covers the semiconductor side inside Volkswagen, semiconductor strategy, semiconductor reliability, which is very interesting to see. In a car company, you do have now dedicated people to do that. So he's a semiconductor strategy and reliability assurance activities head in the company, which is inside the electronic development portion of Volkswagen Group. He has been there since 2011. His activities concentrate on technology capability enhancement of most advanced nodes, as well as optimization of power electronics integration for automotive applications. Andreas is active in various societies, in electron devices, in CPMT, that's packaging, in nuclear and plasma sciences, in reliability and solid-state circuit society. You will see that reflected in his talk. He is an active person in JDAC as well. He is part of JDAC 14.2, and since 2007, he chairs the German VDE ITG group. Recently, he has been also chairing the European chapter of the Global Automotive Advisory Council. Again, an important one, and as we bridge more and more to the automotive domain, and we saw many papers, panels, and so on in the automotive track. So I'd like to welcome to the stage Andreas Aal.
Thank you very much for the nice introduction. So first of all, I'm honored to be invited here at this very interesting conference, and I hope I can bring a bit of value to you. Looking at a different perspective, you have probably not much experience in the past. So what we see is the product. So I refer to previous talks. It's the sum of all efforts. That's nice. Unfortunately, also the sum of all failure rates leads to the product of the reliability function. So looking at the terms of product optimization, it's also very important to understand what's behind and how the construction foundation of a car is, and you will see that the foundation of the car is moving more and more towards your domain. So we will talk about functional safety and cybersecurity today a bit, mainly in terms of what does it mean in terms of electronics integration into the car, and also the influence of the actual architecture in the electronic system. So I will first spend a few minutes on the automotive total quality management principles and the automotive transformation that's going on right now. Then I talk from an automotive perspective, from a vendor perspective, about the design risks that are coming out of the semiconductor product design. And also then, I make it easy for you, I go to real-life examples. Examples that are related to system-level design and parametric deviations, something regarding packaging and assembly, and something that is related to IP integration and automotive. So then I will move to Gina Pasras. This is not a nice Indian lady. You will understand later what this is. It is a very important initiative along the supply chain, and then I will conclude. So 90% of the innovations in automobiles have their origin in electronics. So from that perspective, you see there is a new statement. Who are we? We are a software-driven electronics manufacturer and mobility service provider. At least that is what we are becoming and what we have to become. And the heart of it, and key importance, is the semiconductors. Because the semiconductors, they enable the software needed for the user functions in the car. They enable, of course, data collection, and the data is the new oil. So it's very simple in principle. So therefore, our business strategy has to change. Coming to the fundamentals, I think it's very essential learning to speak the same language, and it's very often very important to have the same definitions up front so that we are sure that we are talking about the same things. So in automotive, the total automotive management principles are performability engineering. That means we're looking at functionality, we're looking at sustainability, and we are looking at dependability. What does it mean actually? Something regarding we have to have availability, the function needs to be ready when called. We're talking about security, strongly also on this conference, protection against intended deviation, and we're talking about fault tolerance. On the other side, we have the sustainability side that is coming from the reliability, that is clearly designed towards specified load conditions. And I got yesterday the question, what are load conditions in automotive? Load conditions are in principle the sum of all mission profiles consisting out of the manufacturing history of manufacturing the part, plus the environmental stress profile, plus the operation profile that is also related to the overall construction. So here we have a defined specification. So what happens if the actual use condition is beyond that? And when the system can withstand this specification or this conditions out of specification, that is what we call robustness. We have a robust product that can withstand something that is beyond what was originally designed. The next part is resilience. That means we have the ability of the system to adapt to some changes in the load conditions. That's very important. It's also related to what you call resilience here in this conference, and we have to have that also in the automotive domain. And all are related, of course, to functional safety. So having said this as a basis, is it better now? Thank you. Having said this, some appetizers are up front. One towards cybersecurity. A system is cyber safe if and only if there is a justifiable and enduring confidence that it will function as expected when expected. So what does it mean for an architecture of distributed easy use of a car of today, where we have limited knowledge about the inside, a kind of black box situation? You can infer that it will getting more and more difficult. So that means from a functional perspective, we cannot afford anymore, looking towards security, to go on with the architecture, and we have seen it within the NXP talk also yesterday, as it is like today. And we have another issue also that is related to lifetime, that is firmware updatability. When we're talking about enhancing security algorithms, changes going on, then we need to update also eventually semiconductor firmware. How often can you do that? How is the relation between this software and the hardware inside? So that also leads then to the fact that the overall strategy needs to change. So that means we cannot test a network of black boxes unless behavioral models are accurate. So who designs those models? The next thing is a change of the meaning of testing and test engineering. Test is already an integral part of the product design, but also it is a looping process. So I would say it's an aggressive statement, forget the V model. It is established, but we have to think in different ways. We have a looping process, so that means we have to change the requirements based on what we get from testing. We have to adapt the test to achieve or to see what is actually going on. We have to understand the system, and we have to do the right things right. So that is a clear message here. So compliance to security means less complex architecture, and replacement electronics for sure is a concept of that. The appetizer towards functionality, to functional safety. I'm happy that I brought this picture in here because I heard just from the last talk that it is a requirement to have Moore's law available in the slides. As I'm the first time here, I see this is a kind of different representation of Moore's law, so therefore I'm safe. So what you see is actually here, because of the innovation that takes part also driven by the integration of material configurations, we have, of course, achieved that tremendous performance increase in the semiconductor and in the software industry. But at the same time, when we look also in the manufacturing lines, and you see that we even also have to understand what's going on the complete supply chain, that we understand that the tool chain that is available in the semiconductor industry as of today has limits in terms of detectability. So that means when we're talking about a 7-nanometer manufacturing line, and we're talking about reliability defects, that means we cannot detect them anymore. So how do you risk assessment when you can't detect what's going on? So you see, it's very, very important that understanding also the type of defects that you need to capture with your electronic methodologies that you design into your IP or in your general methodology. So this is something that we need to look at. But there's also another message. You can test a lot, but can you compensate everything? So it's also about improving from the learning process. And that's it's a clear message here, what we see, because we also do benchmarking of fabs. Now I'm talking especially the newest nodes. Contamination control is the essence also to improve and to learn and to get better yields. And that is related to controlling the air, controlling whatever is in contact with the wafer, and of course the chemistry itself. And there we are talking about parts per trillion. Yeah, so we work also with partners from the supplying industry to have the assessment competence to what's going on. It is important for us because it means that our product design needs to work with eventually higher defect density levels. And this is also a cost factor, but be prepared, do your risk management. So the automotive transformation in principle means simplification and complexity management. You see on the y-axis the time, and you see on the x-axis the degree of change in architecture that is driven out of the functional requirements that enter from the non-automotive domain into the automotive domain. And you see from that we have seen also the version of NXP yesterday from the distributed ECUs towards the computer version up to also to the zone computing. Of course, there are various stages in between. Important is this is a stepwise process that is going on in the automotive industry that needs to be aligned with the semiconductor or with the electronics industry in principle towards, of course, a high computing system that is driven by operating systems where the functionality is coming from software. And when you increase the software content by software updates, it also means it's not just a fix or a change. It means you increase the number of functionality in the car. So it's a complete new function, new concept you have to take into your design environment and consideration. So unfortunately, doing this just from a functional perspective does not necessarily address all the issues that arise from a reliability perspective. So just to run short about it, so from an automotive vendor, when we deeply look into electronics and assembly options that we get, we see, of course, they are very, very complex constructions. Mechanical engineering plays a role. We come from mechanical engineering just on another size level, of course. We understand that the assembly process So the history of the device during manufacturing and also is, the various players in that field and the materials is getting more and more complex. We have several lessons learned out of, say, non-aligned activities here together with automotive load conditions as discussed before. So safety is very much depending on, because testing cannot compensate for gaps in the design for reliability aspects. So you need to understand the failure mechanisms to design around or to monitor and to define actions. Of course, last but not least, the third part is testing, and we discussed also yesterday regarding 3D testing that there are quite challenges even in the consumer domain towards 3D testing. If it comes to, say, a very complex construction in the automotive domain, things getting more and more critical, and I will show you some examples afterwards. And of course, today, qualification, if you look at, say, traditional test scenarios, you need to rethink. Are those conditions now damaging? Are they actually appropriate for this new system? And we had very, very interesting discussions during this conference regarding burn-in of multi-chip packages, multi-chip modules, and so on, where you have various technologies coming in. So you really have to go into the depths to understand what's going on. So, and simulation, of course, is now an integral part of qualification and assessment, risk assessment. And there we have also a huge amount of need to understand from a system level perspective what's going on. So going to the first real examples, as I stated, the function we require is bound to the technology node or the technology, and the technology, of course, is bound to the initial key product design, which is not coming from automotive. That is the case as of today. Reliability and performance of those technologies are under risk under automotive load conditions, and we can principally categorize these in stress exceeds strength, so from a material construction, CTE, mismatches, and so on. And the other side is that we have parametric deviations, where we have also different classes that are event-driven, and then they are reversible, that they are event-driven, they are not reversible, and so on. So it's getting more and more complex, but you have to say, to really understand what's going on. One example is shown here. As a symbol, you have a parametric distribution in the final test, very tight, fine, and then you have fails in the field. And these are examples from 3 different IC vendors we had in the history, and it took us 2 years to investigate, to do the root cause analysis with the help of the supply chain to adapt actual functional testing on the board. And what we figured out, the distribution of those parts that were originally like this, after the whole construction ended up to be there. So that means the manufacturing processes afterwards that are not in your hand can have a tremendous effect on your part, on the functionality of your part, so the parameters. And we figured out, this is what I can say, that mechanical stress plays a huge role in this. So especially in advanced nodes, here are some examples from IRPS or from Intel in principle, that as you thin down the chip inside the package, the severity in the active area towards changes, parametric changes increases. And in the reality, it goes down even more based on the experiments we have performed. So after having done that, those 3 vendors didn't allow us to publish. They didn't allow us to say, we have a problem here to the industry, let's solve it. They feared that will affect their business. So we had to do our research on our own to say, now we can publish, now we can state, we have a problem here in the industry needs to understand this. So what we did is, in principle, we tried to mimic the situation we had in this conservation cases. So that means the interconnect work in the chip after soldering, and the conservation after solidifying of the solder joint made a stress conservation in the chip, and depending on the actual layout, that had effect on the active area. At the beginning, people said, you are crazy, that is not possible, we never reached that stress levels. Doing simulation, doing experiments has proven otherwise. So What we did here was a nano indentation on an SRAM chip while it is running. And in order to increase the sensitivity, we performed the read-disturb procedure by bringing the SRAM chip in an under-voltage scenario, just at the limit where the bits would flip. So that means we repeat the measurement, we see, okay, it is now in a 0 or a 1 stage, and what happens if we apply mechanical stress. So it's just a trick to figure out what say, a mechanical stress can do. So what we figured out then was with a scenario where we actually applied a statistical methodology, repeating this many, many times, you could really see a correlation between the indentation point and the probability that at those positions the bit flips. Yeah, so we also later go on up in voltage, do the measurement again, and so on. So with a dedicated procedure, we could, for the various stresses, we could make, say, a correlation. And we could apply this actually then to a complex package design, meaning especially we could identify what is the effect of placing the copper pillars at various positions, because the interesting thing was, once you press from top, it is the distribution of the position of the copper pillars that affects whether you reach 1 gigapascal in the active area or not. So that is one thing. So it's just to prove what the real fails, the root cause that we had in the field was proven by this methodology. Okay, the next one is related to solder joint reliability in the overall construction. We looked here, we looked at the component level, we looked at the board level, and we looked at the system level by really applying a new measurement methodology that allows us to measure local CTEs on the board. By this, we can with partners here in the European project, we can create local and global deformation maps in the system. So this is not thermography, this is really a map regarding deformation on the board. And there we had very interesting results, so that depending on the amount of temperature shocks you're using and also on the temperature you run, you get various different maps, which in principle means that based on the mismatch of the CTEs of the materials, we have really something going on in the material, and it is really depending on the board layout, on the placement of the boards, of the stiffness of the board, and so on. So this was done on experimental setups. And the outcome was actually that we have a huge influence whether we have a freestanding situation, if we mount it with screws, if we tighten it with the board, with the housing. This was simply experimental with a test board. The actual situation we did then with a real application, and the key message I would like to bring is, so by doing the same tests, the board level tests that are usually applied in the industry by applying IPC standards, for instance, that show that the cycle to failure decreased by a factor of 10 just by screwing the board into the aluminum housing. So this is especially related to QFN or BGA packages. So this is also a clear message. We didn't have these issues years ago, but then we had also smaller boards. So it's obviously strongly correlated to the placement and to the size of the board and also the bending. So what we need is design rules where to place screws and so on, the simulation foundation for that in order to cope with this complexity, or we need to change our complete design methodology at all, just as a hint. So the last one is related to digital IP. Some functionality we need to add in digital IP to be automotive compliant. And the only message I would like to bring here is that is related to environmental or operating conditions out of automotive that technology dependent. We need to add something to compensate for certain failure mechanisms that otherwise in the consumer domain wouldn't play a role. So you do that, of course, and this is an example out of the European project on the RTL design level where you include the resilient IP. This was the same project that was also related by the Mentor Graphics presentation where you saw from ST Microelectronics this interesting monitoring methodology that was also done together with Volkswagen in this project, and we learned also from that what you can actually achieve by doing so. The problem is, this is an older example, but it shows in principle, you take those methodologies, those to be resilient, and now you have to combine it with the real situation. So simply taking what is already available is not sufficient. You have to re-evaluate it, and then you figure out you have a redundant path, but actually now due to parametric deviation because of thermomechanical load, this more sensitive path reacts, and now this is a sort of source of failure in automotive. This is exactly what you don't want to have. So the last thing, example shows here that by aging a board with microcontrollers with BGA solder balls, we actually say with the help of the European project and also with Schaub Electronics, which is a partner from Volkswagen, we established a methodology, measurement methodology based on the bit error rate test scenario to detect very early by repetitive measurements that there is a nano crack evolving in the solder ball, and the effect is that the bandwidth of the PCI Express, for instance, can change here. So it is very essential, especially for autonomous driving, to understand what bandwidth do we require, and is there something that can affect this bandwidth? And we have, say, shown here also there is something going on. Research is further going on, but we have to look at in order to be sure. So this is just an example saying here it's a continuous degradation. It's hard to see at the side of these QFN packages, and you have a crack evolving here with a number of cycles, and you can see this actually in the statistical representation of the eye diagram. So the detection level can be very low, at least in these first experiments we have performed. The last thing I would like to address, and this is very much related, and I'm very happy to this, that I found this mindset at this conference, is collaboration. Most of the achievements so far, as I recognized, came from we have to work together. And in the automotive supply chain, and as we also know, have the role to drive this transition, to drive the different architectures, we need to collaborate. We need to work together with the semiconductor industry, and this is actually not so easy from a legal perspective. So what we have done is that we founded the Global Automotive Advisory Council in SEMI. It was also announced 2 days ago that Volkswagen is now SEMI member. And we have created a legal framework that is called Platform for Automotive Semiconductor Requirements Along the Supply Chain that is based on US and on European law in principle as a guideline that allows to form chapters and platform per world region where, say, companies along the supply chain can discuss about technical issues that they have in common. And the beauty is that there is, say, also reporting infrastructure, and that the council, with the standardization organization, with the expert groups, with road mapping organizations, will define memorandums of understanding to have a clear view how can we in which way communicate information and how can this bring value to the whole chain. One example here is that, for instance, as of today, the AEC, JITR, JEDEC, the ECPE, and EEC, they are developing standards towards silicon carbide. This is not helping whatsoever. So we need to define, you have to do something regarding power module qualification, the other technology, the other power MOS. So we need to guide the industry to do the right things and that we don't have different viewpoints and standards, and this is very essential. So this is the outcome of all of this, and this is the role we would like to support in the interest, of course, from our company, but I think it serves well also the industry in general. So this is what I have in principle stated. The task is really to connect, to collaborate, to include also the whole supply chain from the semiconductor domain related to non-competitive issues in mutual interest to all of us. So to conclude, in order to control complexity of the electronic product car, as we say, service provider, we have something new going on. An architecture change is mandatory. At the moment, the industry struggles to do this transition. Therefore, we have this initiative with the platform, and the GINA, I forgot to say, this is a global initiative, New Automotive. This is related to all organizations that are not yet linked to this GAAC, but they are going on worldwide, and we try to contact them and say, align them to have a straightforward procedure. We are moving into a new ecosystem, and we need the help of this ecosystem to be an integral part of it. And I think testing is the essence of that, because testing is the basis also for the improved design, as we also for autonomous functionality testing, continuous testing and monitoring. I say SBIST, system level built-in self-test. This is something what we need. And of course, testing always needs to be rethought in a new environment. So from that perspective, thank you very much for listening, and I'm open for questions.
Thank you so much.
No questions?
Excellent talk.
Thank you very much.
I'm sure you'll have more questions during the break, though.
Yes, no problem.
I'd like to present this to you.
Thank you.
Something very special.
Thank you.
Congratulations, and look forward to have more interactions with Volkswagen.
Does it work with
Thanks.
Google Translator?
Try it.
Yeah. Thank you.
Otherwise, we have help.
Yeah.
Yeah. Thanks. Yeah, as you see, we are expanding our automotive presence inside ITC with numerous kind of talks, including the workshop that we'll have later on this afternoon, starting at 4 o'clock, the Automotive Test and Reliability Workshop, which will be part of the program. Now, we saw, of course, Andreas' talk. With ITC Test Week, I promised you at the opening session that we'll have 6 visionary talks. We have done 5 so far. We're getting ready for the 6th. We saw the 6 keynote talks. We saw together the Global Test Forum. We saw the pitch tank, the Sky Talks, 1 left this afternoon. We did 5 already. We saw the industrial practice sessions, the application awards, the appreciation awards, that is, we have some more left for this, the ending of this session, as well as we noticed the memorabilia wall downstairs and the test books. Now, I'd like to see if you like this much so far. Was this good? Thank you. Okay, glad that you liked it. However, many of those things are not part of the proceedings. So we thought we'll be sharing some of this information for you beyond ITC to continue with you, okay? First, I'd like to thank the steering committee of ITC. The steering committee was extremely supportive of all these projects that you saw. They were part of creating all of this, delivering it, and so on. So I'd like to individually thank each one of them. Excellent work. I'm sure you notice how much volunteer effort is behind all what you see here at ITC. In addition to the steering committee, we've got help from an organizing team as well in numerous newer aspects of ITC that we offered this year. So we needed the help of additional valuable volunteer resources, and I really appreciate their individual work as well. And hopefully we'll see more of them in the coming years, helping ITC become even more successful. The sponsors. The sponsors of ITC are very important because they are the ones who back us in all this effort. IEEE and IEEE Philadelphia section are the sponsors of ITC since the beginning. Actually, since the beginning, we also had the Computer Society with us until a few years ago, where we became 100% supported by IEEE Philadelphia section. The president of IEEE Computer Society, unfortunately, she was unable to be with us due to health reasons. Professor Cecilia Metra sends her best regards and wishes a successful ending to our conference and continuity for the coming years. Speaking about IEEE Philadelphia section, I'd like to point out two very critical individuals who helped us a lot as well. Marvin Weilerstein. Marvin, are you with us here? Yes, Marvin is there. Please acknowledge him. Marvin has been with the steering committee for many, many years, at least a decade, if I remember correctly, even more, representing the IEEE Philadelphia section in the steering committee. This is his last year in this position. I'm sure we'll see him at the next ITCs, but not in this position. Replacing him in this position, representing Philadelphia section, will be Peter Silverberg. Peter is here. He was the previous president of IEEE Philadelphia section. He'll be representing the section in the steering committee as well, and will be enjoying their support in coming years. Also, we enjoyed the corporate support of Mentor, Synopsys, Advantest, Teradyne, Cadence, financially making our conference very successful. Also, on the celebration and the awards part, we show particular support by Synopsys as a patron as well. Now, having said all these appreciations, I'm coming back to the point that I made earlier. We have continuity. So if you like to see those presentations, especially the keynotes and the visionary ones, we will have a dedicated special issue of Design and Test on the 58th ITC. Will come early next year, and we'll have all these 12 talks and a little bit more in that special issue. So please look forward to that. In addition, though, we'll have the video recordings of these talks on our website. So again, look forward to that. We recorded all 6 plenary sessions, and therefore you'll be seeing on YouTube the 12 keynote and visionary talks. Also, if you're on social media, you may have seen that lots of what we're doing here is being broadcasted live on Facebook. So we have Facebook Live of most of the plenary sessions that we were here. You can also, if you missed some, you can look at them there. Or if you want to listen it one more time, you can do that too. Okay? So this is for the coverage and the continuity. Now, now it's time to hear our last visionary talk of ITC, the 58th ITC. And this will come from Advantest. And we're very pleased to have Keith Schaub with us. Keith is the Vice President of Advantest for Applied Research and Technology. He has been very active in the field of semiconductors for 25 years. He's been part of several startups, so he comes with a small company and large company experience. He consulted on RF system architecture for several Fortune 500 companies. Keith has also multiple AI-related patents and papers in NLP and VR for enhanced test engineering debug, for smart auto RF matching load board, automated robotics, smartphone production testing, and AI and machine learning for anomalous defect classification in this case. I'm sure we'll see some of that in his talk as well. Keith, please. Let's welcome Keith.
Okay. Well, so first of all, Yvonne, thanks for the invitation. I'm very glad that he asked if you're enjoying the show before my talk. So the good news is this is the last visionary talk, so you don't have to listen to it anymore. The bad news is this is the last visionary talk, so all the visions have already been done. Several years ago, I was giving a lecture somewhere in Asia, and I was teaching this class, and after an hour into it, I asked if anyone had any questions, and not a single hand went up. So I thought, I'm an amazing teacher. An hour later, same thing. I asked, do we have any questions, and no hands went up. Then I thought, I must be a natural. At lunch, I was very excited to tell this to the organizer, and talking about the class and all the material and how everyone is absorbing the slide set, and she stopped me and she said, Keith, I'm sorry, nobody understands you. We don't speak English. So she saw my deflated look and she threw me a bone. She goes, but we really like the pretty pictures that you draw on the board. Okay, so my name is Keith Schaub, and I'm actually the Vice President of Business Development. Vice President of Applied Research is actually Ira Leventhal, sitting right behind me. But what we do is we develop new and emerging technology, and we integrate that into our services and products. And the reason that we do that is to expand our customer value. So what I'm going to do in the next, 20 minutes here is I'm going to talk about some of the megatrends that are going on in the industry and how that relates to this Industry 4.0 that we find ourselves in. And once we have this landscape, I'll highlight some very specific use cases that could be a part of the semiconductor industry as we move towards a data-driven future. So let's start with the past. If we were to summarize test in one sentence, we'd probably come up with something like, we test to collect data. And we've been able to do some amazing things with that data. We automate our entire test cells. We have yield learning. We gather all sorts of statistical information on our automated process. But we're not able to truly realize the full potential of the data. And that's primarily because the data is siloed. It's behind different customer clouds. The data is often in completely incompatible formats. And we don't have the tools to easily reflect those changes and move data to where it's needed. So that's really hindered us from taking advantage of all that this Industry 4.0 has to offer. However, the future, what we believe is going to start happening is we'll start to see all of these data lakes that are currently siloed tied together. And it'll probably be tied together with some sort of super data highway. And Stacy Ajuri from TI, she gave us a glimpse of what one such possibility called RITDB. But whatever the case may be, once we tie all of these together, and then we can apply machine learning on top of it, we'll start to have all these new insights and new intelligence that frankly we just haven't had access to before. And that's going to change everything. So instead of the past where we tested to collect data, the data itself will actually tell us how to test. So instead of testing to collect data, the data will tell us where to test, how to test, when to test, and what tests are needed. And we'll start to be able to answer very important questions that we've had for quite some time, but we just weren't able to answer them. So questions like, how do I optimize my entire test flow to get a specific yield with a specific cost? How should I distribute my tests across that test flow? And what would happen if I move this test from insertion A to insertion B? How does that affect my cost, my yield, my coverage? What if I add test? What kind of yield improvement do I get? Or what if I remove this test? What does that do to my coverage? So these are the sorts of questions that we'll start to be able to answer in this data-driven industry. So let's start with big data. You've probably seen a slide like this before, and you hear someone say, like, in the past 2 years, we've generated more data than in all of human history. And that's a mouthful, and that means there's a lot of data. And it's estimated that in the next few years, we'll be generating 44 exabytes of data per day. So I had to look up what an exabyte is, but I don't know who created that number or where it came from, but obviously whoever did it hasn't read Hitchhiker's Guide to the Galaxy. Because if they had, that number would be 42. So how much data is that? Well, if you convert that data into DVDs and you stack it, that's 5 billion DVDs per day. And since we're in Washington, D.C., I converted that to the number of Washington monuments. That's 36,720 Washington monuments. It would reach out into outer space. So the point is, we don't really have a good reference. We need something global to wrap our heads around how much data this is. So, wrap our heads around it. Let's wrap it around the Earth. It would take 7 days for us to complete the circle around the Earth with the DVDs. So maybe we should start calling the amount of data that we're generating in terms of Earth bytes. So we generate an Earth byte of data every week. In any case, I think we all are in agreement, it's a nearly infinite amount of data when you think about it. And that data, as you can see from the graph, is the kind of fuel that's driving these megatrends. Megatrends such as 5G and IoT and cloud computing and artificial intelligence. And all of those trends, they actually feed off of each other. So as one of them grows, it pushes the others to grow. So you have this snowball effect. And the snowball shows only signs of increasing in velocity. So we've reached, one of the other visionaries 2 days ago, he was talking about this push-pull. And we're in that pool where now we need to start taking advantage of all this new technology that's available, like big data and machine learning, analyzing that. So it's interesting if you think about where does all this data come from? Turns out half of the data comes from us, just walking around in our smartphones. Shouldn't be too surprising because smartphones are nothing less than supercomputers. And supercomputers have a way of generating tons of data. So that's about half of that data. Well, about the other half comes from this IoT, the Internet of Things. And the Internet of Things, you can sum that up as billions and billions of sensors connected all around the world, all the time, everywhere, transmitting wirelessly across our 5G networks. So that's a lot of data. And that data has to go somewhere, which is into these cloud farms. We have these cloud farms and cloud servers all over the globe. But the data keeps growing. The applications keep growing. The 5G networks keep growing, and they all feed upon each other. So we're in this age of this industry era 4.0. So now that we have that as a landscape, let's do the vision stuff. Let's put and map 5 specific use cases that we may see in the semiconductor industry in the next several years. And I'll briefly describe them here, and then we'll go into detail of each one of them. So the first one, understanding customer benefits. With all of that data and all of it tied together and using the machine learning techniques to create new business intelligence and insights, we're going to understand our customers a lot better. And we're going to understand our markets and our trends a lot better. So how do we do this right now? You've got experts in various companies, and they spend their entire lives looking through financials and listening to quarterly calls. And they're the gurus. They use their crystal balls to predict where the market is going, where the inflection points are. And then they advise the R&D organizations to place bets. And it's gambling. It's a bet because nobody knows. And the confidence levels, if you ask, who knows? It just depends. I would say we're as often incorrect as we are correct. And this has an adverse effect on our industry because now we're all risk averse. We don't want to spend the money because it's just as likely we're going to be wrong as we are right. But imagine that that's going to change and our insights are going to give us high confidence that our investments are going to pay off. That's going to just further accelerate this industry. So this is a very good time to be in the semiconductor industry. The second one, decision making. So data is power, and with that data, we'll be able to much more effectively make decisions, and we can make these decisions near real time. And we can use that data strategically and operationally, and I'll talk about a very specific use case. The third, improving customer value proposition. So what is that? Well, we deliver testers, but we want to deliver smarter products, smarter capabilities, and smarter services. So we want to take this data, apply machine learning, integrate it into our products, and improve the value to our customers. And that will in turn allow our customers to improve their values. And I'll talk about a very specific use case. One of my favorites, and according to my CO, it should be the favorite, monetization. So data as an asset. Well, data is an asset. Recently in the European Union, they passed the law that it is forbidden to use your data without explicit permission from yourself. So they've recognized that your data is highly valuable, and if somebody wants to use it, they have to pay you for it. They have to compensate you for it. So this will drive new businesses and services that we haven't been able to achieve yet. And I'll talk about one very specific to Advantest. And the last one, automating key business processes. So I'm sure almost every one of you in this room has experienced the hurry up and wait in our industry. We have these highly automated test insertions, test processes, whatever you want to call them. They're highly efficient and highly automated. But in between, not so much. Our ability to develop automation in these in-between areas is going to be one of the additional advantages to drive inefficiencies across operations. Okay, so let's get into it. The first one, understanding customers better. So it's a bit complicated. It's all about test challenges. Imagine that we have access to all of this data. We understand these trends much, much better. We have insights into our customers much, much better. Well, we're going to understand our customers' drive to and beyond the 5 nanometer process and how post-silicon, wafer, package, system level test, burn-in, how they all play a part, and we need to orchestrate them in order to meet the requirements that our customers need. And understanding the entire supply chain's cost challenges. So we're really good at understanding our direct customers' cost challenges. Where we're not so good is understanding our customers' customers, or our customer's customer's customer. So all the derivative of those, we have very limited knowledge and experience with. But that's going to change, and we'll be able to provide products and services that help that entire supply chain. Understanding how quality improvements drive automotive. So Andreas, he's setting me up really nice with that. So with autonomous vehicles connecting into our 5G networks, well, our smartphones are hosted on the 5G networks. All the IoT devices are hosted on the 5G networks. So it's only going to be natural that the quality requirements from automotive, which are more stringent, are going to push into those other customer spaces. And how are we going to deal with that? Well, we're going to deal with that by utilizing all of this data. We're going to be able to make better decisions, how to balance and optimize the test flow in order to push those quality requirements onto those segments without adversely affecting the cost. And last but not least, understanding 5G. So it's not just another G. 3G to 4G, if you compare the innovation going from 3 to 4 versus what we have to do to go from 4 to 5, it's a step function. What we did from 3 to 4 was an incremental innovation versus what we're having to do to go from 4 to 5. And that's primarily driven by these three: phased arrays, over-the-air, and millimeter wave. All three of these are mature technologies in our cousin industry in the mil-aerospace. They've had that for years, but not at the cost points that we need, and certainly not at the volume scales that we require. So again, we're going to have to take this data and these insights, and we're going to have to leverage what our cousin industries have done, innovate on that technology to bring the cost down, and then deploy that at scale. Now, sounds like it's hard, and it is, but we already have done this. We did it in the late 90s when we first put RF onto our ATE testers. People said, oh, it's too expensive, it can't be done, you're going to go out of business, and in 2 years, we had production solutions. And look where we are now. So we did it before, we'll do it again. The second use case is decision making. So imagine in the near future that you will be able, with reasonable accuracy, with just a few measurements early in the process, you'll be able to predict the yield of the wafer. Imagine how that's going to completely change volume planning or supply chain management. So right now we have these huge peaks and valleys when yields suddenly drop off, and our supply chain is forced to absorb that. It's very costly and it's very inefficient. But imagine if you had a priori knowledge that your yield was going to drop in a month. You don't know why. You just know it's going to happen. What would you do? Well, obviously, you'd go ahead and start additional wafers. And how would that affect the supply chain? Well, the supply chain would maybe feel it as a ripple. So instead of these huge spikes, it would all get averaged out. And that's going to help our entire industry run much smoother, much more efficiently. And it might sound like magic, but this has already been demonstrated by the fabs. This has already been proven. And we know that it works because next generation devices are the children of the previous generation. So they share an enormous amount of DNA. And just like the child and the parent shares DNA, if you have measured the parent across this entire test flow and collected all of this data and have all this understanding of the parent, when that child is first born with just a few measurements, you can make very accurate predictions on how that child will perform or how that child will yield. Terms like overcapacity and underutilization as problems, they may start to disappear. The third use case, improving the customer value proposition. So we talked about smarter products, smarter services, smarter capabilities. Well, in the oil and gas industry, they're already deploying this into their production. So it's proven technology, they've proven the models, they've proven the ROI that they get from it, and they're deploying them into their production facilities. What are we going to do? We're going to leverage that knowledge, use our fleet of testers. We have thousands of testers full of data, run that data through those models, and we can do the same thing. And we could perhaps offer that as a service or as a product to our customers. And you can see all of the benefits that the customer chain or the supply chain would have. You'd have smart replacement, decreased planned maintenance. You would have a situation where testers don't go down right in the middle of a very important high-volume run. The asset would always be available. So it's interesting. So if any of you follow Amazon, Amazon's working on this software, this predictive software. And what it does is it predicts what you're about to buy. And they go ahead and they ship it to you before you even buy it. So you'll get out of bed, open your front door, and there'll be a box from Amazon. And you'll open it up and go, wow, I didn't know I needed this. But I'm going to keep it. So maybe in the near future, well, and you'll say, thank you, Amazon. But maybe in the near future, our field service engineers will show up at your production door with a module in hand before you even know you needed it. And we'll replace that module, and the system will never go down. And you'll say, thank you, Advantest. So one of my favorites, this monetization, again, data as an asset. And we said data is an asset. And how can we use that data to drive new businesses and new services? So perhaps you've heard the term in the Industry 4.0 called digital twin. So digital twin is where you create a digital replica or a digital ghost of a tool or an asset, and you host it in the cloud. And then we could offer that as a service or as a product. We could lease it. We could sell it to customers that want to run their data through these virtual insertions. So we could have multiples of these. We could have a wafer virtual insertion, a package virtual insertion, a system level test virtual insertion. And the customers could actually run their data through all of these insertions and get a very good predictive understanding of how it's going to perform through each of those stages. What's it going to cost? What's it going to yield? If you knew before first silicon that you were going to yield 18%, Is that valuable to you or not? I think so. So other benefits that could come from this are a completely optimized test flow. You as the customer could designate what your target yield is, what your target cost is. And the flow could be completely optimized to give you that target. And think about that, because that's important to you depending on where you are in your product life cycle. If you're brand new and this is a brand new product, all you care about is yield. You want to get product into your customer's hands. So you would perhaps optimize the entire system for yield. But if this is later and it's a very mature product or it's an aging product, and now all of the competitors have caught up to you and you're under extreme cost pressure, then maybe you would like to re-optimize the entire test flow for cost. That's possible with this type of service. And the fifth and the last is automating and improving business operations. So we talked about hurry up and wait, and automating some of those processes. So I think Mike Campbell gave a visionary talk, and he talked about how he has 300 engineers, and they're bogged down in the tedious minutia of this manual scripting and converting and all of these things that have nothing to do with engineering. And he wants to offload that and upskill those engineers so they can work on truly test engineering tasks or product engineering tasks and not have to deal with all this underlying minutia. And if you haven't seen it, Professor Lee Si Wang has some software. He's demoed it a couple of years here at ITC. It's called AYA, Intelligent Engineering Assistant. And what it does is it uses machine learning to look at a bunch of wafer data and give you insights into that data, suggestions, recommendations, things to go look at, things that you might be concerned about. So applying that logic here, this situation, or this scenario that's represented here on the slide, we're looking at perhaps a new RF product, and it's being brought into production. It needs to ramp on the new wave scale RF that we have. And if you haven't ramped something before, you know that it's plagued with problems and issues. It's the first time that you're putting everything together, the load board, the socket, the chip, the test program, the handler, all of these things, it's the first time it's being put together. And it takes a tremendous amount of effort from the engineers to get that into production. If you're lucky, it takes several days, but it can take several weeks. So what if we had an intelligent assistant, and this would be the proverbial Jarvis that's helping or assisting Iron Man. So this would be an assistant that is specialized in a specific skill set. It could be RF, it could be high speed. And this intelligent assistant is monitoring the entire scenario. It's looking at the inputs, it's looking at the outputs, it's looking at the interactions between the engineers and the test system itself. And it's not solving the problem. It's making suggestions of where to look. In this case, it's suggesting there perhaps is a ground issue on pin 14, and the confidence interval is 63%. So you as the engineer could go off and check that versus having to just search through all the possibilities. And you could imagine that if this were available on our fleet of testers, which there are thousands of them, how fast with reinforcement learning these assistants could rise to perhaps almost an expert level. So all of that minutia that we have to deal with right now as test engineers and product engineers, that could be absorbed by these intelligent agents. And we could offer that as a product or as a service. And even third parties may come in and do that, where they build their own for some special hardware that they've developed. So my last slide, in summary, Advantest has a 10-year grand design vision. And in this grand design vision, you can see in the middle is our core. That's where we came from. That's our final test, our wafer test. And we're working to go left and to go right. So I guess I should go left this way. So to go left, we're working with the EDA tool vendors, and we're linking those tools together to provide extended capabilities in the go left strategy. In our go right strategy, we've got our newly acquired Advantest test solutions, which build system level test and burn-in test. And we're mapping all of these together and overlaying it and connecting it with cloud, AI, and data analytics. So you can see that all of the use cases that we've described here actually fall into this strategy. So it could be that in the next several years, we may start to see some of those in reality. So with that, I say thank you.
Thank you so much.
Thank you.
That was excellent. I have the pleasure to present this to you. It's a piece of art for you to carry.
Can I get one more?
Let's do this.
I want one more without my glasses.
One without the glasses. Thank you.
Thank you.
Okay, thank you. I appreciate that. Let's take this. A couple of small points. One of them is several of you, as I gave the 12th beautiful plaque, the manuscript, wanted to see what's on it. So I photographed one of them for you to see how does it look at least. So now you can see how does it look at least, right? But again, one day if you are here to give a keynote or a visionary talk at ITC, we may be able to manage one, okay? But these were, again, manuscripts that were created based on Middle Age illuminated manuscripts from Armenia done in the monasteries by the monks. So exactly same design, same skin, it's animal skin. The colors come from plants or insects. And each one of them takes 10 to 15 days to prepare. So it's a piece of art, but dedicated to the person because it carries the name of the person on it. This is not Keats. This is Andreas' one. As you can read, it's Andreas. Okay, in case you're interested to see the real ones, Smithsonian Museum here on the mall has several of those older ones from 900, from 1020 or so, that are in their collection. You can have a look at them if you are interested, okay, as you're in Washington. In case you miss it this year, I'm pleased to let you know that next year we'll be in Washington again. So then you can see it next year. Now, in the appreciations, so I'd like to appreciate, we covered lots of authors, papers, and so on. Now I have the pleasure to appreciate some of our exhibitors. We have our oldest set of exhibitors that have been with us for a very long time, the oldest of which has been with us for 43 years. I didn't start with Advantest because Keith just finished his visionary talk. No, just because this is alphabetical order. So that's why Advantest comes first. We do have a number of companies that have been with us. We like to thank them all, to appreciate their presence, and to look forward for future years to work together. Now, I'd like also to thank all of you as participants. You have been here with us throughout the past 3 days, 5 days, including tutorials. We have one more day with the workshops, so your participation is very important. And active participation, whether on the floor or on the stage. Your active participation was very valuable. Here you see Andreas giving his keynote. There you see Davide Appello, who will be giving a keynote. This is in advance. He'll be giving a keynote at the Automotive Test and Reliability Workshop. Now, I said that we'll have more information through social media. You can look at those as well as you go forward. The last two individuals that I'd like to extend my appreciation to are the ones who have served the longest period on the steering committee of ITC. And that's really impressive. And that would be 32 years. Ken, correct me if I'm wrong. 32 years, Don Denberg, who unfortunately is not with us today, but he served throughout the year with us as well on the steering committee since 1987, as well as Amy Gold since that time as well. And both of them started from their childhood, of course, on the steering committee and helped us a lot throughout those years. The third person who immediately comes after them is Ken Mandel. Ken, please stand up. And we'd like to thank him as well. With our appreciation, again, for over 30 years of service to ITC on the steering committee. Now, we know that we don't finish here. We have next year to come, and we'll be also in the same room, in the same hotel, between November 1st and 5th, okay? This will be the 51st ITC, and Peter Maxwell will be our general chair for next year. He's already preparing. Peter, are you here? Yes, please stand up. This is Peter, who is carrying the ball for next year, and we'll appreciate all the good work that he already started doing. Jennifer Dvorak, Jennifer will be doing our program chair position. Jennifer, are you in? No, she's already working. Okay, so she's not here, she's working on it, but deadlines are here though. So please try to remember those deadlines and try to submit your papers. With that, I'd like to thank you again, and now back to the sessions. Thanks.